Okay, we are live. At least I like to believe that we are live. Um, we'll see shortly. So, joining me today is an extra special guest. And I wonder if you just might say something about who you are and what you do for those who might not be familiar with your work.
Hi, I'm Gualtiero Piccinini. I've worked a lot on computation and cognition, but I have broad interests in philosophy of mind and related sciences and related areas of philosophy. So I started out primarily with investigating what does it take for a physical system to implement computation, because I wanted to get to the question of whether the brain and the mind have something to do with computation, and went from there.
Very cool. So, also, before we go too far into any of those interesting topics you just brought up, you also started the Brains blog. Is that correct that you started it, or I know you were managing it when I discovered it, but did you actually officially start it?
It's yeah, I think it started in 2005, and initially it was just my blog, and then
Ah,
Dan Ryder, I believe, suggested turning it into a group blog because there wasn't really one in philosophy of mind. So I did
mhm.
that, and I started inviting anybody who wanted to contribute. So it turned into a group blog, and then after a while, I gave it to John Schwenkler to manage for some time. Then he gave it to others, and yeah, it's definitely become a really nice venue, I think, for exchanging ideas in our area.
I agree.
But
Yeah. No, it's very cool. I was just gonna say it's where I got my start blogging. I guess there was kind of a golden era of blogging in philosophy for a certain period of time. Maybe it's not
yeah,
quite as at the peak as it was anymore, but I think Brains is still going strong. It's definitely making a
yeah,
contribution.
yeah. It's more structured now. They have editors and they organize, symposia and
Right.
sessions, but it's good quality.
Yeah, I've been happy to see also their collaboration with the Neural Mechanisms Project
Hmm.
and the kind of online mechanisms conference they have. So it's been very cool to see the direction that that's taken. But also, like it was very nice that invited people. And I remember when I first reached out to you, and you were like, "Yeah, come on, go ahead." So you were very welcoming, even to junior people such as myself who didn't. I felt even at that time I was like, should I even be posting online? So it was very much a welcome to be felt included in something at that level. So that was definitely appreciated.
Yeah,
Okay.
absolutely. I mean, I've always tried to create opportunities for more people to exchange ideas and to be included in a profession that historically, of course, there's a lot of underrepresented groups. There's still work to do in that area, in that respect. So,
Absolutely. Yeah,
I don't know
exactly.
if you're familiar. Are you familiar with the International Society for the Philosophy of the Sciences of the Mind?
I've seen something about that actually, but I haven't really paid attention to figure out what it is. I've been doing really busy, but it's on my list of things to figure out what it is.
Can I tell you?
Yes, please.
So, there are these more regional and more specialized societies like the Society for Philosophy and Psychology. But as far as I could tell, there was no society for the sciences of the mind in general, like the philosophy of the sciences of the mind in general, including all of them, psychiatry, neuroscience, the biology of behavior.
Ah, interesting.
And also, there wasn't one that was truly international. So I got together with Ines Hipólito, who's a originally Portuguese philosopher,
Hmm.
and we founded this new society. And the goal is also just to keep it virtual. So it's all going to be virtual conferences.
Ah,
And we've already done the first one last fall, and it went really well. And the call for papers just came out. So if you look it up, if you Google, International Society for the Philosophy of the Sciences of the Mind, there's a new call for papers.
okay.
The deadline is going to be in a little while. I don't remember the exact date, but there's time. There's
And
time
it's
to submit.
virtual too, so it's online. Oh, interesting.
And the reason is that way anybody from anywhere in the world can participate without having to pay for a plane ticket and accommodation. even if they're disabled, even if they have little kids, even if they're from the global south.
It's true.
So even if they're just students, I mean, obviously there's the selection process, but we try to keep it inclusive. The quality, I thought the quality was really high of the
And is the
conference.
material still available online from that first conference?
I don't think that they recorded everything. They might have
Oh, okay.
recorded some keynote
Oh, so
speeches,
it's actually
maybe.
like web conferencing. Because
Yeah,
like when I did the online conference, I remember what you were a part of too, but it was mostly like, like post on a blog and then discussion in the comments section. But this sounds
yeah,
more like actual face to face.
yeah. It's a real web conference, and
I see.
we try to have slots that are compatible with different time zones. So some things, are easier to follow in North America, some sessions, and some sessions are easier to follow in Asia.
Okay.
Um, it
Very
depends on
cool.
the session and the participants, but we try to keep it accessible to everyone.
Well, I'm all for these kinds of ideas, so I'll have to look more into it. I know last fall I was working on this alleged book of mine on higher order theories and neuroscience of them. So I wasn't really, I even took research leave. I mean, I don't want to, we don't need to discuss all that. But anyway, I wasn't even teaching. I was just trapped up here, just working on that. So I was really out of touch, but now I'm kind of getting back in touch, seeing what's out there. So this is very interesting. I'll make sure to put a link to it in the description of this once it's all up and stuff like that.
Yeah, yeah,
So the
and yeah.
ISPS, International Society, MPS, International Society for the Mind Sciences,
But the philosophy of the
ISP.
science of the mind, so PSM, ISPSM.
PSM. There you
Hmm.
go. Okay. Very cool. And it's good to see this kind of stuff. Just to plug the more written format, I still encounter graduate students or persons that I talk to online who say that they've been to the online consciousness conference. The material is still up there, and they'll
Hmm.
ask me when this comment, when David Chalmers said this, and you responded like that. What did you mean? And I was like, whoa. So it has been interesting to see that having that written material and the exchanges, the comments, and everything up there, people still use it, and I find that gratifying. So, well as I value face-to-face interactions as well, I think that there's something to be said for the other. Um, but anyway, I don't want to get distracted by that. But people should check out this. Is there any way that people who are not presenting at the conference can attend it?
Of course, yeah, and it's free too because
Okay,
it's online, so the costs are very minimal so far. I hope it
perfect.
stays either free or close to free. So you just have to register and you can attend whichever portions you want.
Okay, well, I'm very glad to know about this, so I'll pay more attention to it and keep it in mind. So now turning to your book, which I guess is this book a couple years old now, or when did this book come out? The Physical Signature of Computation.
No, the physical signature computation is coming out this summer.
Okay, it
So that
hasn't
one
come out yet.
is brand new. Yeah.
Okay,
Yeah.
I
I
see.
also I also have a book called Neurocognitive Mechanisms that came out in 2020. So
Right, that's
that's
the one I was thinking of.
recent, but at this point, not super duper recent.
I see. Okay, yeah, I was getting them mixed up because I was reading both of them recently. Um, it's a lot of stuff, but I find this stuff very interesting. So, I mean, just generally, the idea that the brain is a computer or has some information processing or computes or something like that. I think people like you and I find that commonplace, but maybe less surprising than you used to. But I still teach like an introductory neuroscience class for non-science majors. So and when you and I teach it from kind of a cognitive neuroscience standpoint. When you tell them this, the idea that the brain is a computer, a lot of them find it almost unbelievable or like comical or oh my gosh, what has science got itself into or something like that. So I wonder if you could start by motivating the idea generally that the brain computes.
Yeah.
Why do you think this is an interesting thing to think about? In other words, is what I'm asking.
Yeah. Well, it's a long story, but it does start with a few observations and analogies. There's a myth that it starts with Alan Turing, but it doesn't really
Hmm.
start with Alan Turing. It starts with Warren McCullough and Walter Pitts, who were what we would call now neuroscientists. And McCullough in particular was the senior one. He had training in philosophy as well as psychology and neuroscience, and he noticed that there's this tradition of mechanical manipulation of symbols, including logic, going back to at least Leibniz, and then going through Babbage and Turing. And he knew about Turing's paper on computable numbers. So he thought, if we can map that kind of logical machinery onto the brain, we might understand how the brain does it. So in his case, he really did think that it's a kind of digital computation that involves manipulating language like symbols. Okay, what came to be known as the language of thought later on. We're talking about early 1940s. And from there, once you have full-blown digital computers, you have the fact that they're general purpose, that by exchanging a program, you can add and subtract abilities. And our brain is very flexible, capable of many different things. So how is that possible? One possible explanation is, well, it works kind of like a digital computer, switch programs and you can do different things. Now, the problem with that idea is that even though it's plausible, at least on the surface, and it provides an explanation that we didn't have before, it's actually not very plausible once you look in the brain more closely and see how it actually works. So from that idea, there are different routes that were taken. One was just focused on the programs. That's classical computational psychology. Figure out what the programs are, and then you'll have explanations of behavior. But then another route is the one of computational neuroscience, cognitive neuroscience, computational neuroscience, that says, no, actually, let's figure out how the brain does it, which doesn't mean that it's not doing something like computation, but it might be a different kind of computation. Mm-hmm. It might not be digital, and it might involve, a lot of training and retraining and learning of how to build internal representations and process them at the same time. So I think the second route is the one that is both plausible and promising. Mm-hmm. And I've defended that, in my own work. But there's still a lot of people who are attached to the first way of thinking. Right. And they haven't really quite figured out that we know enough about the brain to realize that, yes, that's not really the way it works. So to make this really work, you have to have a more expansive understanding of computation that's beyond just a digital computer.
Mm-hmm. And so, well, there's a lot in what you just said that I want to ask. So I'm wondering about going back to these early guys. McCullough and Pitts, and the general idea that the way you try to think of computation as you have a string of symbols and some rules for how to manipulate those symbols. As far as I understand the artificial intelligence movement and so forth, that's been very, lackluster in producing results. And in fact, I don't know if you saw this recent talk by Hinton, where he was basically kind of doing what I consider a victory lap over the kind of language models that they're producing and the style of computation actually that they're producing. So are those the two paths, the kind of things that you meant to distinguish, the symbol processing on the one hand versus the kind of neural networks on the other hand? Yes. And the project of your book is to try to give an account that covers both of them but shows how they're different. Is that basically the idea?
Well, this new book, it's entitled The Physical Signature of Computation. That is something, for the most part, even more basic. It's not so much about how the brain does anything. It's about what it takes for any physical system to implement any sort of computation. And it focuses primarily on digital computation, because that's the arena where this debate has taken place primarily. And also, there's a lot to say right there. But that's not to suggest that is how the brain works. It's just that we're trying to give a more in-depth account of what physical properties must a system have in order to implement a computation. And I'm happy to talk about that, but I'm just saying, That's the project in this case. There's one chapter about the mind, brain, and it does talk a little bit about the kind of computation that's going on there. But for the most part, it's really about these like more basic questions about how many physical systems implement computations, what properties do they have to have, and what
Mhm.
follows.
Yeah.
Um,
Right.
we
So I know
actually
that.
get into something really, fun, and you can find in the popular press sometimes questions about do we live in a simulation, that kind of thing. We end up talking a little bit about that too.
Yes, I know. I want to talk about that stuff as well. But now since we brought this up and we're talking about this, I want to kind of ask you about the PCE, the S, the P, and the PCE, which I think are the main, most of the actions about the PCE part, which
Mhm. Yeah.
that the physical computational equivalence requirement that you have. So since we are talking about this, I wonder, could you say a little bit something generally about what you take it to be, um, for something to be computational and for a physical system to implement a computation?
Yeah.
And then I want to ask you a
Good.
question about it.
hmm Yeah. So historically, there's kind of two camps. Those who think that computation requires representation. So in order to have a computation, physically speaking, you have to be manipulating some representations, whatever that means. And then the other camp is, no, you don't. You can have computations without representation. Now, there's all kinds of subcamps, but in this book, we're definitely in the second camp. And even more significantly, we uncover what we take to be some very important, well, especially one, this PCE, physical computational equivalence. It's a condition that is very important and needs to be satisfied to implement computations, and it has nothing to do with representation.
Hmm.
Okay, so it's really a vindication of the non-semantic type of accounts of physical computation, which doesn't mean that computation does not, in fact, manipulate representation more often than not. It does. That's why we build computers, and our brains definitely, in my opinion, represent things and manipulate representations. It's just that to understand what it takes for a physical system to implement a computation, you have to look at some intrinsic physical properties that have nothing to do with representation. Okay. And I think you were asking me, so what are these conditions?
Yeah.
So one part of this project was to get even more clear and precise about some conditions that have been proposed before, but maybe were not as fully explicit and fully precise as they could have been. Those are, we call S for state and P for process. S for state basically says that for any computational state of a system that's putatively implemented, for any state, any computational state, there have to be at least some physical states from some lower level microphysical states of the system that map onto each of the computational states. Okay. And they don't, and the physical microstates that cannot map onto more than one computational
Hmm.
state. So each physical state that maps onto a computational state maps onto only one, but for any computational state, there's something that maps onto it. And then that's the state condition. The process condition is that for any computational state transition between computational states, in the automaton that's putatively implemented, anytime you're in a physical state that maps onto one of the computational states and you transition onto another um, physical state that maps onto another computational state, it maps onto the right computational state. So the transitions also are mapped to each other.
Right.
Those two things are sort of present in previous literature, but they weren't specified as carefully as they could have been.
That's
There's,
S and
there's
P.
a,
You just went.
yeah, S and
Uh,
P, and there's like more details. So one other very important thing that maybe other people have hinted at in some degree, but it wasn't fully specified, is that this mapping needs to be done basically digit by digit. So if you're implementing a certain automaton and it has multi-digit inputs and states and outputs, it's not enough to have like one physical state mapping onto the whole input or the whole state of the system. you have to have substates or substates of subsystems of the physical implementing system map onto individual digits of the automaton they're implementing. So that's also very important. Okay. But still, all of this is not enough. There's one very crucial condition that has to be satisfied in addition to all of this, and that is physical computational equivalence. And that is, put simply, that any physical state that maps onto a computational state must carry the same amount of information about the computational trajectory of the system as the computational state that it maps onto. So no more information, no less information about the computational trajectory. And I can explain a little bit better what that means if you want me to, but that's the statement. Okay, that's the condition.
And so the basic idea is that you should be able to, I think, as you put it, infer from the physical state the next computational state so that there's an equivalence between them. You could treat them as the same, basically.
Or the predecessors to the extent that you can know them, but no worse and no better than you could if you just knew the computational state and the computational description, meaning the automaton that's being implemented.
So I think this idea is very interesting. And a large part of it seems like you're, at least in this book, you want to distinguish it from other versions that try to ward off the specter of pan-computationalism, the idea that like everything computes. And there have been basic people who have posed this as a challenge, and then various people try to propose a solution, and you find that none of these solutions really cuts at the right level, so to speak, because they can always find a wiggle through it. But then the PCE shuts that door, so you can really say that. I mean, I guess the idea is that if you have a state in the wall that's transitioning between like a shadow or something, you say, that's the negation function. It's like, well, you can't really infer the negation function from the state of the wall, so it fails the PCE criterion. Is that roughly the idea?
Yes.
Okay.
Right.
Yeah, cool. I mean, I find that to be a very interesting idea. And there are things in the details that I would ask about. But just more generally, in this book, what I was wondering, kind of big picture, was what I didn't see a response to the objection from kind of the other side. And what I have in mind, so to speak, is kind of the Kripkean objection. Kripke kind of argues that maybe you could put it that even your calculator doesn't compute, so that if the famous argument that if the calculator fell from the sky, you wouldn't be able to tell what function it was computing, because the state that it's in is always consistent with different computations that might have been implemented by different designers, and without access to knowing what they specifically had in mind when they designed it, you can't say. So I'm just curious if this is something that was meant to be left out, or something that you didn't think needed to be addressed. I mean, I don't mean this as any kind of like attack on your view. I am just curious because I am interested in this argument coming from Kripke, and I noticed it wasn't in there.
Yeah, no, that's a very good question. And before I answer that, it just become painfully aware that we haven't mentioned my co-author. So
oh no, right, I forgot. yes, it is co-author.
I didn't write this book on my own. I wrote it with Neil Anderson, who's a brilliant physical information theorist at UMass Amherst, and I definitely could not have done this on my own. It builds on his previous work in physical information theory. I'm happy to say a little bit more about it at some point if you want me to, but I just want to make sure everybody knows that I co-authored this book. I definitely put a lot of work into it, but I did not do it on my own.
Absolutely. You should have made that clear at the beginning, 100%.
So with respect to the Kripkean objection, if I remember correctly, I'd say a little bit about it in my previous book, the 2020 book.
Yeah, that's what made me wonder why it wasn't in this book.
I don't know that there's like a great reason, but I didn't think that it was important enough to address in this book, because what I think Kripke didn't fully appreciate is that computers are built from components. And so once you go down to the simple components, the logic gates, there's not really that infinite potential for, infinite many possible outputs from infinitely many possible inputs. Like any actual physical machine, strictly speaking, is a finite state automaton. So, and also it can be decomposed into, even if it has the architecture of a general purpose computer, it can be decomposed into these primitive computing components. And the primitive computing components can be tested to death. And they get tested. They get tested, carefully enough that engineers appreciate their reliability under various conditions. So then they can build integrated circuits. And the integrated circuits, they have billions of these components, but they are configured in very specific ways. So you can, if you wanted to, you could reconstruct exactly the exact logic of the whole design and which functions are computed or supposed to be computed by each individual component and then by the whole processor once it's all put together. So, there's interesting epistemic questions there, but there's not really the skeptical challenge of, oh, what does this really compute? There's all kinds of questions about under what conditions does it work properly? Was it designed properly? Was it built properly the way it was intended? Does it malfunction under certain conditions and not others? Is it being used properly? If something fell from the sky, you have to kind of open it up and see, what are the components, and then you test each component, and then you figure out how they're hooked up together. You don't just like take it as a black box. Yeah, if you took it as a black box, you'd have more problems, more serious problems about figuring out what it does. But if you could open it and look at the mechanisms, eventually you would figure it out what the components are and how they're put together, and reconstruct its whole logic design, if you will.
Yeah. So,
Yeah.
yeah, I guess I see what you're saying, that you just don't take it as you take it as a skeptical challenge. That's, I guess you're saying epistemic, not really a metaphysical challenge to say that this, but I guess that Kripke, as I read him, did interpret it as a kind of metaphysical challenge. But yeah, I never know how serious to take these really skeptical challenges. But it does make you wonder that when it comes to the brain, it is kind of something that fell out of the sky in a way. We don't have access to the
Yes.
design scheme of it, the logic gate level description of what's going on in the brain. We're trying to discover that. So I do think that when it comes to thinking about the brain and what if any function it is computing in any given case, that it's kind of more, it presents more of a realistic challenge. And here's one way I would say again. Oh, sorry.
It's a huge challenge. It's very hard to figure out what it does, really.
Yeah, exactly. But you don't feel the force of the idea that whatever function we think we're ascribing to the brain, it's compatible with that series of states, that there was some other function that it was computing. It just so kind of overlaps with this one up till now, which I guess is one way of kind of at what I would think of as a high level summary of what Kripke's point is that there are lots of functions that partially overlap. And so we may be observing a region where there's this overlap and then extrapolating to cases, since it is finite, since the brain is a finite state automaton in some sense of that, we're extrapolating. And this is the idea that you always have to give an idealization of the physical item in question in order to make this mapping between the computational state and the physical state. And every time you do perform that idealization, part of which is what I see in the PCE, then you're making some assumptions about which function, which computation the system is computing, because otherwise you wouldn't know how to idealize it, and what computational level structure you'd want the mapping to map onto. So there is a sense in which you kind of do assume. And I mean, yeah, I'm not sure what to make of that, but I wonder what you think about that way of putting the challenge.
Yeah,
Especially in the context of the brain.
Yeah, so with respect to this kind of like global skepticism about knowing what function is being computed, I'm not really moved by that. I think that it is a matter of figuring out the details, start with the basic components, see what they do, how are they put together, what do their composite systems do, and so forth. And PCE does help because you do need to have a certain kind of informational structure in the physical system for it to genuinely implement a computation or another. But then when it comes to studying, a super complex system like a brain, yes, there's going to have to be some idealization involved. There's going to be a lot of abstraction involved. You're going to have to identify relevant levels. And in fact, even in neuroscience now, there are debates between people who want to focus more on computation at the level of individual neurons and circuits and networks, and people who want to look at higher level variables. They call them manifolds. And so these are abstractions over like larger systems or larger networks of neurons, and maybe combinations of different systems into larger super systems. And so some people are more drawn to understanding neural computation at this higher level, and other people are more drawn to understanding computation at a more lower level. I think they're compatible ultimately. It's not like they're mutually exclusive and you have to pick one. Just like a digital computer has all these levels of organization, they're all computational. You can go below the computation and look at how they're implemented. But even with once you reach the computational level of description or explanation, you start with the logic gates, and then you build and build and build and build. And once you have billions of them, you have to talk about processors and memory components, and there's lots of levels in between. And this is all still machine level. We're not even talking like operating system and application yet.
Yeah, exactly.
So the brain might well have lots and lots of computational levels within it, it's smaller, simpler computing components that are put together to build larger and larger computations. And representations are part of the story as well, especially in the brain.
Okay. Since you brought up the idea of having these components, realizing them, I did want to ask you about your account of realization and the way that you try to distinguish that from, I'm blanking on the term, but I'm sure you'll remember it, but the
flat view and dimension view?
Yeah. So the idea that, well, can you tell us about how it is that these computational properties are going to be realized? That's the basic question that I want to ask in a physical system. And how the intrinsic components of the physical system are going to play a role.
So I'm not sure that I fully understand this question. So if this is the same as the question of how is computation implemented, it's it's the stuff that we talked about before. But there is a broader notion of realization that's used in many debates in philosophy of mind. And in that regard, I think the best way to understand realization is as a relation between properties of larger systems and properties of their components. And my account of realization, which I developed in collaboration with Corey Maley, says that a higher level property is realized by lower level properties, just in case it is an aspect of the lower level properties, the properties of the components of the system that you're looking at. So, could you have a higher level computation, like operating system level computation, or manifold computation in the brain? It might be realized by a lot of processes by individual neurons or circuits of neurons if it's an aspect of what they do. So an aspect is sort of like a part, like a proper part of this larger ensemble of properties. That's what realization is.
Yeah, that's what I meant to be asking about. So I think that's sorry for putting it in a confusing way, but I'm curious about how this account of realization fits with the account of implementation. So that's what I am curious about, how the two relate. So when you say that the brain is implementing physically implementing a computation, but at the same time there are multiple computational levels.
Yeah.
I'm a bit, and then at each computational level has as an aspect something from its previous level. I am a bit curious about how this is all supposed to fit together.
Yeah, good, good. That's great. That's great. You're asking wonderful questions.
Oh, sorry. I'm just confused. I
Um,
don't mean to be asking good questions.
no, it's because I mean there's so many aspects to all of this, and there's so many things to say, and you can't say it all explicitly in every possible way. So talking about it can really bring out some of the interesting details. So the way I think about it is, let's start with like thoughts, okay? Like you're
Mhm.
thinking about stuff or reasoning about something. That's a very high level computation or information process or whatever. And it's going to be realized by lower level computations. So that's an aspect of what a lot of neurons are doing to combine, collectively. Um, but still, even though we call it neurons, they are sufficiently abstract that you could do the same thing in a large language model, or at least like something similar enough. It
Mhm.
doesn't have to be biological. We're capturing something about the computational and representational aspects of the mind or thinking. And it could be replicated, at least to some degree, in a model, in an artificial system, especially if you actually build artificial processing units, aka neurons, as opposed to building a simulation in a digital computer.
Right.
That's a whole other can of worms. But
Yeah.
okay, so we're like realizing higher level computations by lower level computations. Then at some point, once you have reached like something that would constitute primitive computations in the brain, let's say, or on a computer as well, now you can realize that by implementing it into a technology. Now you have to bring in more concrete properties of the physical system that's implementing the computation itself. At that point, in the brain, you're looking at action potentials, ion channels, electrical discharges going through axons and dendrites, and neurotransmitters being released between in the synapses between neurons. So you're going to have a bunch of electricity flowing, charged ions going in and out of membranes, chemicals released in synaptic clefts. That's one thing. But if you were to build it in a silicon circuit, it would be made by other kinds of things. It's just that it would be maybe having some of the same uh, computational properties. For example,
Mhm.
same firing rates or timing of individual spikes might be analogous, and so that's why you might want to say it's performing the same computation. Just like you can build a digital computer out of silicon microchips or gears and mechanical components like Babbage's analytical engine or electromechanical components or other kinds of physical media. So
But
yeah, so
but
there's realization, but at some point there's also implementation, which is a kind of realization, but it's a special kind because you're going from these um, computational properties that are just basically degrees of freedom of the system to the uh, constitutive aspect, physically constitutive aspects, the specific forces, the specific kinds of components, kinds of physical components that actually do the implementing.
yeah, okay. So I see there's a question from Johannes Kleiner in the comments over here. I want to ask that to you in a second if you don't mind. But just really quickly, so which level does the PCE apply to? Because I thought that in order for there to be a computation, there had to be some kind of very strict equivalence between the physical state and the computational state,
Yeah.
defined in the way that we talked about previously. But now there's levels. So where do I go to the physical state and infer the computational properties of the highest level?
Yeah, so it
It seems
applies.
like I would want to go to the next lower level, not the physical level, but some like more abstract computational level.
Well, so where PC applies is in the connection between the kind of um, primitive computational level and the implementation of that, physical implementation of that.
Mhm.
Everything else is taken care of automatically, meaning any higher level computations are going to still basically reduce to that primitive computational level of, like, in the digital computers, it would be logic gates. You have,
Mhm.
like, let's say, and gates, or gates, not gates. So once you implement those faithfully in a way that respects physical computational equivalence, then all the higher level computations are already taken care of and they're all implemented faithfully. Now, this is an approximation in real life, okay? So it
Mhm.
might not be perfectly faithful implementation, but it's it's very close to perfect in digital computers. They're pretty well made at this point.
Okay, so I want to come back to that, but really quickly, the related question. So Johannes asks, "There's amazing conversation. Thank you. Is realization of one computation by another a matter of realizing qua implementation of both computations by the physical system?"
Sorry, can you say that again?
Yeah, so is realization of one computation by another a matter of realizing qua implementation of both computations by the physical system? So I think this is kind of a related question to the one that I was just asking, actually.
If I understand the question, I think the answer is yes. Meaning,
Mm.
yeah, there's higher level computations. They're going to be realized by lower level computations, and those lower level computations are implemented by some kind of physical machinery. Well, when you do that, you're also implementing all the higher level ones as well.
Can you
Um,
infer from the physics states of the physical system that implements the lowest level, the states of the highest level computation?
yeah, you could, it's just that when you have billions of components, and actually making inferences like that would take an insane amount of time. But yes.
Okay, but you are committed to that because it sounded like to me what you were saying was it's just that lowest level that you make these inferences, and then at these other higher level implementations, um, maybe you don't.
No, you could. You
You
could.
could. Okay.
You could. If
Yeah.
you
So
had a lot
that's
of time and resources, you could.
yeah. That's okay. That's very interesting. And so this overlapping aspect thing I wanted to ask you about, and especially because we're going to be talking about consciousness here, so we may as well. Um, oh my, I can't. The time has been flying. I haven't even realized keeping my answer.
I
So I know I can't keep you
know.
forever, but I do want to make sure we talk about consciousness before we run out of time here. Uh, so before we do bring up consciousness, though, is there any aspect of the physical implementation of a computation, putting aside the consciousness bit, which is non-computational, um, that plays a role but is not computational?
Oh, there's a ton of that.
Okay.
So one of the things we stress in the book a lot is that um, to find, an implementation of a digital computation in an ordinary computer, you have to disregard vast portions of the state space of the actual physical system that implements the computation. So this is something that, in my opinion, has been really underappreciated by previous philosophers or philosophical literature. Um, so, I mean, some of it is really obvious. Computers have cases, they have fans, they have electricity flowing that needs to be taken from the electrical cord. Um, so none of that is actually implementing any computation. It's sort of all supportive stuff. But even within a processor, there's tons of stuff that happens that is never mapped onto any computational states. Um, so there's a lot to say about that, but yes, the answer is yes.
Okay. So how do you know which to rule out?
Um,
Because I
well,
remember I'm trying to get my Kripke puzzle back in here, by another method.
Right. So, I mean, obviously, we're talking about artificial systems, so they're designed for this purpose.
But
So
when
in
it comes
this,
to the brain, though, I mean, because I think the real force of this is we don't know what level to focus at.
yeah, but that's one other reason why the brain is not doing digital computation,
Mhm.
and why classical cognitive psychology and cognitive science, where to the extent that they were assuming that it's some kind of digital computation, language like or not, is undermined by neuroscience, but it's also undermined by fully appreciating how digital computation really gets implemented physically.
Mhm.
Um,
So
so
wait, are you saying
how
that
do you
just
know
wait?
in
Are
the
you saying
kind
that
in
these issues don't apply to analog computation?
well, they don't apply the same way, or
Mm.
or, even, I think neural computation is it's sort of its own kind.
Oh,
It's
right. We haven't got to that
I
yet,
I
right?
use the term neural computation, which I take from computational neuroscience. But yeah, Corey Maley, for example, he prefers to call it analog computation, and he draws an analogy with certain kinds of other kinds of machines. I think that can be helpful. Um, but you don't have this exact same kind of issue of disregarding some of the states that you do with digital computation. So the power of digital computation comes from the precision that you can achieve by stringing together all these digits. But to do that, you need to have these states to be stable, so you can recognize them, reliably as zeros or ones, if you have binary code. Um, so to do that, you need to stabilize the state of these components. But components, like physical components in an electrical or electronic circuit, they're not naturally stable. So you have to do a lot of fancy engineering to keep these things stable enough during the right kind of time intervals,
Mhm.
and uh, and therefore, all the stuff that happens to make this stable has to be disregarded as not really part of the computation itself. So, the state of a capacitor can fluctuate, in voltage, and it only counts once it's stabilized around either like the 0 level or the 1 level. Um, and so you're going to have this signal, it's called a clock signal, that
Mhm.
goes through the machine, like lots and lots of times every second, that determines when you can check the state of these components. And so therefore, when it counts for the transition to the next state. But when you get the clock signal, it counts. When you're waiting for the next clock signal, it doesn't count.
Yeah.
So it's all built into the how the machine works. The times when it counts and the times when it doesn't count, the places where it counts and the places where it doesn't count.
So,
And that's very important in physically implementing digital computations.
yeah, I agree. But it's just so since we brought it up, can you tell us what is your view of neural computation that's distinct from like what people like Corey want to call analog computation and also digital computation?
Well, so uh, I'm okay with calling it analog computation in
Okay, you
Corey's
are. Oh,
sense. I don't think that we have to call it analog computation. We can just stay with and neural computation. That's the term used in the field. Um, and I think there is a more restrictive notion of analog computation that's also useful, and neural computation is not analog in that sense. Um, but one thing to point out to understand how different it is from digital computation is that there is no clock signal, and there's nothing analogous to a clock signal in the brain. There's a lot of synchrony, but it's a synchrony that comes in degrees. It's very important. I mean, it's not fully understood exactly how much, but it's understood that synchrony between components is very important to neural processes and neural computation. It's just that it's not synchronized by like a centralized signal that says when things count and when they don't.
mhm.
Instead, it's sort of self-organized synchrony that comes in degrees, and it counts even if it's out of phase. So it's synchrony as in like I do this, then you do this. I do this, you do this. So it's not like they're happening at the same time, but they're just happening in partial synchrony. So they kind of
Mhm.
oscillate together. There's a lot of this in the brain. and it comes in degrees. So yes, it needs to be understood, but it's very different from the kind of precise, guaranteed synchrony driven by a centralized clock that happens in a digital computer. So this is just one difference. There's other differences, but yeah, it's another important difference is that the signals are also graded, but neither fully continuous nor fully discrete. So, in a digital computer, you would have finitely many possible states, period, typically two, 0 and 1. In an analog computer, in the strict sense or the restrictive sense, you have these fully continuous signals that you have to integrate. But in a typical neural system, you have spike trains. What matters is the frequency of these signals, the number of spikes per second, and that can vary, and they do need to get integrated to some degree, but it's a whole different process of integrating these inputs, because you have to sort of combine all these different input frequencies to decide whether they pass a certain threshold, and then your neuron is going to fire again. And so you really need to understand the way this system works in its own terms, I think.
And you don't find the idea of trying to map on the way that digital computation works onto this structure would be fruitful or useful?
Can you say that again? I'm sorry.
Yeah, so I mean, I agree with you that. So it sounds to me like what you're saying and what you've argued for in your work is that we look at the brain and we find, well, the things that you've been describing, and they don't clearly map on to the notions in digital computation for various reasons, and you've just listed some.
Yes. Yeah.
But there is a way of like making it the case that it does in a way if you disregarded certain states of the system, and if you imposed a kind of clock. I mean, maybe we'll discover one. Maybe you said timing isn't exactly going to play that role, but maybe there's some as yet to be discovered way in which these are clocked. And many people have, and I just want to hear your point of view. I'm not really pressing this, but some people look at the binary nature of the action potential itself and at reaching the threshold as a way of reading the binary states. And so it's an open question whether it's synchrony, phase locking, or whether there's a kind of code in the spike trains themselves. Or at a lower level, maybe it's in the dendrites. Maybe Stu Hammerhoff was right, man. It's all in the dendrites. So I think a lot of these questions are open, but isn't it still also open that we could map on to the functioning of the brain or discover that it did implement digital processes, even in all this messiness? Or do you think that's just ruled out given what we know? There's no possible way to do it.
I think that we know enough to conclude that that is not a fruitful way to pursue, or like that trying to find digital computations of the brain is not gonna work, and it's not gonna be a fruitful way to invest resources. There's plenty more that we need to figure out about brains do work, but it's not going to be digital in any useful sense. Now, one important partial exception is that there are going to be some high-level processes, like neural processes, that approximate things with some kind of quasi-digital structure. For example, when you process linguistic inputs, they're still going to be encoded in these complicated neural manifolds, but at a high level of a organization or abstraction, they're going to have something corresponding to the kind of quasi-digital properties that language has,
Right.
like a human language. It's not going to be written in some kind of digital code, but it's going to be encoded in neural states. And even oral language, even though, like when we speak, even though it's all continuous vibrations in the air, our own brains are able to kind of parse that into words. Okay, so words have a kind of digital structure, and
Mhm.
even within them, they have kind of phonemes, and then within sentences or paragraphs, they have their own distinction between word by word, and also even higher level grammatical structure. So yeah, of course, some of that is going to be encoded in neural states. So in certain cases, there's going to be something that has quasi-digital representational structure.
Okay, interesting. So Johannes is asking again in the discussion if neural computation for you is a case of Turing computation, but it sounds like the answer is going to be no, given what you've been saying.
Well, it's going to be presumably Turing computable. So in the sense that you could approximate it, with respect to the functions being computed, you could approximate it with a digital machine like a Turing machine, but it's not going to be digital like a Turing machine.
Okay. So the brain doesn't implement some version of a Turing machine either, then, on your view.
Right.
It can't be
Yeah.
theorized in that way.
No. But, there's been this debates about whether the brain has like hyper computational abilities. Can it compute functions that are not Turing computable?
Right.
And I don't believe that. Although there are a lot of interesting subtleties there. And we could talk about the mathematical objection to machine intelligence. This is something that Turing talks about. But yeah,
Yeah, I do want to talk about that, but I want to get back to talking about the brain and how you think it computes because
mhm.
I still, so just to kind of sum up, I remember trying to get my understanding of this up to yours. So what you're saying is you're happy to describe what the brain does as a kind of analog computation, or in any ways, whatever you call it, it's not digital computation. And one of the reasons why it's not digital is because it doesn't, well, the physical processes that the brain uses to do what we think of as its job don't seem to be the kind of processes that map clearly onto the structure we would expect to find in a digital computer. Is that a way of sort of summarizing the case?
Yeah. Mhm.
Okay. Yeah, very interesting. And then in the case of the brain specifically, now sort of turning to questions about consciousness, um, I know that you end up kind of saying in this book, especially in chapter 9, which of the physical signature of computation book, where you talk about the mind and consciousness in particular, but you end up saying that consciousness is not computable. So in other words, that a simulation of the brain wouldn't have phenomenal consciousness, or at least that's the way I understood it. So is that, first of all, is that the right way to understand the thesis of that part of your book?
Yes, except I wouldn't say
Okay.
it's not computable because that makes it sound like it's hyper computational.
Okay.
That's not what I'm saying.
Well, I mean,
I'm
it's not a computational process fully.
Yeah, it's not just a matter of computational processes. Yes, there seems to be something else going on as well, meaning that's not just a matter of computing.
So, is it the case that a simulation of your brain would have consciousness according to your view?
No.
No. Why not?
I mean, it depends on what you mean by simulation, but if it's a
A
if
digital,
it's a
yes, I
computational
should have
simulation in
specified.
a digital computer, no, it wouldn't.
But you
Why
did just
not?
say that you could Turing that these things could be approximated by. I guess the key word is approximated because they can't be
No, no,
actually.
no. But what I mean is that, neural computations could be approximated by a digital computer, but consciousness is about more than neural computation.
Right. No, I understand that. What I
So
was saying
so
was
that
it's
more that whatever else is going on, it's not automatically reproduced in a digital simulation of neural computation.
can you give us your reasons for thinking that this is the case?
Yeah. It's really a version of some of the classic objections to functionalism or computational functionalism. Um, And, there's married a color scientist and all that kind of stuff. Um, the the way I think about it is that there are causal powers that objects have, and there are qualities or categorical properties that they have. And there's interesting questions about exactly how those two things go together and fit together. But we need both to account for our ontology in general. It doesn't even have to involve consciousness. So I think that ultimately computation is a matter of causal powers. In fact, there are abstractly considered causal powers. They are basically degrees of freedom and how they're organized together to generate more states from previous states, inputs and states, generate other states and outputs. But to get consciousness, it seems to me, you're going to need the qualities, the categorical properties. You need that to account for the qualities of the world, and you need that to account for the qualities of our experience. So exactly how they fit with the causal powers is an interesting question that I haven't really thought through. But it's not going to be just a matter of having certain causal powers, period. It's going to have to be combined with the right qualities. So if you have the right qualities, great. But what it takes to have the right qualities, I don't know. So I don't think that just doing the computation, which is the causal power, certain causal powers, in fact, very abstract causal powers, is enough to get you the qualities automatically. Maybe under certain circumstances, if the causal powers are organized the right kind of way, the qualities come with them for free. But that remains to be seen exactly what those conditions are. And maybe they're not just come for free. Maybe you need something different. You need certain chemicals in the mix, or you need certain degrees of synchronizations between the components, or some configuration of the components. It's actually very hard to think about that stuff.
Yeah, I agree. But what I'm wondering is why. So, um, so for example, David Chalmers is a dualist, but he's
Mhm.
a computationalist in the sense that he thinks the laws of physics guarantee that the right computations bring around the right qualities.
Mhm.
Those qualities aren't identical to the computations, but the computations being instantiated in any way, I don't, as far as I understand his view, almost any way, I think maybe has some stuff to do with Russellian physicalism might come into play. But barring that stuff, if the computations are instantiated in whatever medium, then that they're the qualities come. So I wonder what your objection is to that way of thinking about pairing the two. So you get the qualities and you get the computation and you get a law that connects them. So you get to be a non-physicalist. I mean, maybe you don't want to be, but it sounds like, you
I
know,
don't. I mean, I'm a physicalist, but I also don't see any reason to believe that once you have the computations, you have the qualities automatically.
well,
I
what
mean, if
about your
we,
standard? So yeah, what about your standard dancing and fading qualia type thought experiments where you replace a part of your brain with a computer, let's even say a analog computer or a kind of some kind of artificially instantiated device that did what the brain does, but wasn't biological. So you could have two different versions of this. You could have it's a digital computer you replace your neuron with, or it's a weird neural computer that's not biological. Um, so what is your
yeah,
response to the classic fading qualia argument? I'm curious about that. Do you just think that
yeah.
these kind of a priori things don't matter, or?
Well, I definitely don't think we can figure this out a priori.
Mhm.
Well, yeah, with respect to fading qualia, the question is, you suppose you replace a bunch of neurons with some artifact that computes the same functions. Then the question becomes, is that computation enough to also generate the experience that we normally have, when we perform those computations,
Mhm.
or does it not, or is that not enough? And as far as I can tell, we don't really have a good answer to that question.
Mhm.
We don't fully understand what it takes to uh, generate the experience itself. But one thing we know is a lot of these computations can be done unconsciously. Even in the brain, a lot of computation goes on unconsciously. So just because you're replacing the computations doesn't even, to me, suggest that you would automatically replace the experience. Maybe you're replacing the computation period, and the consciousness goes away because it's involves something else that we don't fully understand. Maybe you need certain chemicals in there or something. And so once
Mhm.
you have the chip instead of the neurons, you do the same computations, but without the conscious aspect. I'm not saying that's the case because I don't know. I'm just saying I haven't heard a good reason to think that just because you're replacing the computation with something that does the same computation, thereby you also, replace the experience with an equivalent experience.
I guess the standard reason would be that to deny that puts you in a very skeptical position with respect to your experience right now, having to admit that you could be having dancing or fading qualia and not know it as we're speaking right now. And that seems to be a kind of radical kind of skepticism that you could be cognitively out of touch with your conscious experience to that degree. So the non-skeptical
Well,
conclusion is that the experience is the same between the replacement.
yeah, I mean, so I think I understand why you say that, but it seems to me that that begs the question in
Hmm.
the sense that, it's built into the way the experiment is, the thought experiment is defined, that there's no noticeable difference to the subject,
Right.
or at least like they wouldn't be able to express it linguistically. Um, but that is an assumption
Right.
that is not really motivated empirically in any way. Like there's no reason to believe that if you actually did try to build an artifact that replaces some neural computations and can be plugged in instead of the neurons, that there would not be any noticeable different to the subject. So I mean, I don't accept that part of the
Right.
thought experiment as given. I think that that's questionable, and it might not work that way.
Right. Because in a way, like to accept that that assumption is already to think that um, they have the same causal powers. But I think part of your
Exactly.
thesis is that it's not clear that this is part of the causal power of it.
Absolutely. So,
Yeah.
yeah, you can build the thought experiment in that way, but then now we don't know if all it takes to keep that experience alive is to
Mhm.
just do the computations, or you would have to have an artifact with additional physical properties that are the ones that are required to preserve consciousness
Yeah.
besides the computational ones. Yeah.
Okay. Very interesting. And so I like this idea that you could be a physicalist and still think that there's some kind of quality involved. But I am curious about why you say that we need it anyway. So, and you said not even about consciousness. So, when you're talking about physical qualities,
Mhm.
can you tell us what it is? And I know you talk about this a lot, but can you tell us what you mean so we can discuss it a little bit?
Yeah, yeah. So I think I mean the same thing that somebody like John Heil means, or even somebody like David Lewis or
Mhm.
David Armstrong mean, when they talk about categorical properties. Now, they may or may not have been thinking about consciousness at all, but
Well, Armstrong
um,
was, and yeah, Lewis too,
oh yeah, I mean they definitely did think about it, but they were also concerned
but
with
not in
broader
this case. Yeah.
questions about, yeah, metaphysics. And so they actually tend to be categoricalists. They think that properties are categorical first, and then, dynamics or behavior come out of that, and maybe in combination with the laws of nature.
Hmm.
And I don't go that far, but
You're not a truth
certainly
maker
there's,
theorist.
what did you say?
I said no truth makers for you.
No, truth makers are fine. I'm just
Okay.
not necessarily a categoricalist, about properties. I don't think that properties have to be just categorical, and
Mm.
then, behavior and dynamics come
So
out of
there's some
that. Plus,
structural and dynamical
yeah, there
properties.
might be there. I mean, I like this hybrid view that properties have categorical and dispositional features, both of them.
Interesting.
Um, but exactly how they go together, I don't know. Um, but I don't think so. What I don't think is that dispositionalism is viable, that it could just be dispositions or causal powers all the way down.
Hmm.
Um, and I think that maybe David Chalmers sometimes thinks that way, or a lot of people in philosophy of mind think that way. They just discuss the things in terms of causal powers, high level causal powers, lower level causal powers, how are they related? It's not just causal powers though. There's
Right.
there's categorical properties somewhere. Um,
So no, you're against structural realism or ontic structural realism, as it's sometimes put.
yes.
Okay. So does this put you in the category of the Russellian monist? Is there a way to say what you're saying without being in that category?
That is another excellent question. I think Russellian monism is often described in ways that are mm,
Too consciousnessy?
maybe not entirely faithful to both what Russell
Huh.
actually thought and maybe what I think is the best way to think about it.
Okay.
I So I know there's a paper by Barbara Montero called Russellian Physicalism, I think,
Yeah.
and where she argues that Russellian monism really ultimately is a kind of physicalism. I don't think she's the only one who says things like that, but I remember reading this paper a while ago,
Yeah.
and I think that is the right way to think about it. And the little I've read of Russell himself sounds to me like that.
Hmm.
So to me, it sounds like what all he's saying is there are these categorical properties in the physical world. Science cannot tell us exactly what they are because all we can see is how they interact with each other. I mean, how objects interact with each other. We can't just kind of go inside the object and then feel how it is
Yeah,
inside, so to
exactly.
speak. But that doesn't mean that these things are conscious or mental or they have qualia or even proto-conscious or proto-phenomenal, if that means anything. It just means they're categorical.
Hmm.
They're not just dispositions. Yeah, we observe the dispositions, but from the dispositions we infer that there's something categorical there that's manifesting these dispositions in certain under certain conditions. Um,
Hmm.
so I
Yeah,
think
interesting.
that's all that Russell is saying. And then, yes, once you put together a lot of different things in complicated ways, you might develop, conscious experience, but that's not something that's sort of built into the fabric of microphysics. It's something that emerges under special circumstances.
Yeah, very cool. And I'm a great fan of Barbara and her work. And she was at the Online Consciousness Conference from back in the day as well. So I'm a fan of that paper. But so this is what I'm curious about because when you say that consciousness has a non-computable aspect to it, and then also you have this kind of general Russellian picture in the background. It does sort of sound like there's some proto consciousness in these in categorical properties or something. So is it your view that these categorical properties are importantly related to consciousness in any way? Because it does sound like the answer is yes
Well, I think they're related to,
to
everything.
everything.
They're
Right.
related to everything. It's like the world comes in many levels of organization,
Mm.
and there's new stuff, um, being created all the time, by organizing components. So,
Right. But I mean,
subatomic
in the more, in
particles.
the, sorry, go ahead. I didn't mean to
No,
cut you
subatomic
off.
particles form atoms, and the atoms form molecules, and the molecules form macromolecules. The macromolecules form all kinds of things, all kinds of structures, including under special conditions, cells, and then the cells can be put together into multicellular organisms. So, every
Right.
time like you have more organization, you get new properties and new qualities. And maybe at some point, some of this amounts to conscious experience. But it's going to
Okay,
be,
so
it
consciousness
seems
is
to me
going to
that's a
come
special
later.
case. Yeah, oh, much later and very special case, not the norm.
And it's not going to be somehow distinctly relate. So this is sort of okay. So a while back, I asked about whether there was any kind of categorical or intrinsic thing that wasn't going to be like computational,
Hmm.
that wasn't related to consciousness. And part of the reason I had for asking that was what we talked about, but the other part was so that I could talk about it here. Because it does sound like what you're saying is that there's a certain sense in which these categorical properties are importantly required for any kind of computation. And that in that sense, like you couldn't create a digital simulation, not just of the brain or consciousness, but of anything in the physical world that we live in, actually, because of these categorical bases. So any digital simulation is going to leave that stuff out, and therefore you're not going to be able to have this kind of concretely simulated environment, let alone whether we could be in there and interact with it. So maybe this is what you were hinting at earlier about the simulation hypothesis. This is the way your view impacts on that.
Yes.
Yeah.
So, right, of course. So, and this is actually our ordinary experience with simulation. So simulation is a dynamical representation of the evolution of a physical system without the actual categorical properties of the system. It's just
Mm-hmm.
a representation of what's happening, and it's not going to reproduce the actual physical categorical properties of the system at all. Um,
Unless you, so here's where I always have the sticking point on this kind of way of thinking. And I saw some exchange with you maybe on Facebook about this point, which is interesting. And it relates to the idea of the simulation of a computation.
mhm,
So there's a kind of line of thought that comes from traditional quarters that when you simulate the computation, well, that is a computation. So
mhm.
a simulated computer is a computer on this line. And your
Mhm.
view is that no, not all simulated computers are actually computers, or at least that's what it sounds like you're saying.
Well, what I was trying to say is that even in simulating a computation, you may or may not reproduce all the causal powers or the causal features of what you're simulating.
Mm-hmm.
So this is kind of a much more specialized point. Um, and that's because you are now using, say, code to tell your computer, your simulator, how to manipulate representations of the states of the target computation that you're trying to simulate. Um, and the reason this is relevant is that even if you were a computational functionalist about consciousness and you thought consciousness is just about computing the right things and performing the right computations, a digital simulation of that might not be conscious
Mm-hmm.
because a digital simulation of that would not necessarily reproduce the relevant causal structure in the target computation. Because you're just using code and representations of the states of your target and using the code to process those, but the states themselves are not connected in the right causal way, the way they would be in the target.
Mm-hmm.
So that's not really my view, but there is this brand new paper by Derek Schiller, I think,
Yeah, that's who. Yeah.
the exact name, where he makes a case that even if consciousness has to do with computation, we need to look at more specific constraints on what it would take to implement those computations for real as opposed to just simulating them, something like that. And
Right.
I agree with him. I agree with him. I think that's a breakthrough in terms of our understanding of computational theories of consciousness. And I don't subscribe to a computational theory of consciousness, but if I did, I would go along with what he says there.
Right. And the idea is that even if you simulated, just as you said, the same computation, that it might
Right.
not, the simulation might not produce the same causal structure. It might leave out
Right.
certain elements of it.
Yeah, and I
Um,
think it's plausible that if consciousness has to do with computation, it has to do with like the computation actually being performed, not just being simulated in a digital computer where it's manipulating representations of the computational states. Like the computational states have to be actively causing each other in the right way.
uh-huh.
Um,
So there's so much we're pushing up against reality here. But let me just ask you, as we're winding towards the end of this, because I have kids that are getting off the bus at 3, so I can't be late for that. Whatever else happens. But so, do you take this to have any bearing on the it from bit kind of physical theories that people?
yes,
Yes. Okay. So they can't. Okay.
yeah. It from bit
Okay.
is a goner. So we have a whole chapter on this stuff,
Yes.
I don't know if you had a chance to look at it, but it's chapter 8, and
Yes.
we go through like every attempt that we have found to give any kind of substantiation to this it from bit idea, and we don't really find a lot of merit in it.
Uh-huh.
I mean, we do think that there are interesting analogies between physics and computation, and it can be illuminating and it can be used, and that's totally fine. But if you try to take it seriously, that, physics itself is at bottom computational, there's not much to that.
Okay, so the selling point of this book is it will rid you of thinking that we may be in a simulated world. Although, so it sounds like if you were like presented David Chalmers' argument that you have to, wind your way through and some level of credence in these in the proposition that either I'm in a simulated world or there's some defeater for that. It sounds like the view that you've worked out is trying to put its finger on what could be the defeater for that, but also still take seriously the idea that computation is involved in cognition and all the things that we find are important.
Yeah.
And trying to, that's what I find very interesting about your work, whether you agree with it or not. And a large part, I find it interesting and compelling, not all the way, but I do think I'm a fan of this work. But it's trying to thread this needle, this very interesting line between saying computation is important, it's real, the brain does it, it's an important part of our science of the brain, but at the same time, it's not the whole story. We've got to be clear about how it's physically realized, what the brain itself is doing that pays homage. After
It's
it's so
certainly
refreshing
not,
after this long march of people saying, screw the brain, it's all about this higher level. And now people are kind of
yeah,
coming to this. Huh.
right. No, it's definitely not the whole story about the physical world, and probably not the whole story about the brain either. Yeah.
Very interesting. Okay, so I do have to wrap up here and let you go and live your life, but I do wonder just at the end if there's anything that maybe should have come up but hasn't come up, something that you thought maybe we ought to have talked about. The answer can be no, but I always like to check at the end if there was something on your mind before you came.
Well, I just hope that people, if anybody's listening up to now, do you get the idea that there was like some substantive um, work to be done, and there's still more to be done on understanding computation itself physically. And it really helps us think more carefully about all kinds of issues about metaphysics, physics, and the mind. So
Yes, very cool. Well, in that
that's
note,
what
let
we
me
try
thank
to do.
you for joining me. I really enjoyed reading your book and having this discussion. I learned a tremendous amount, so I think it's well
Thank
worth people
you.
paying
Thank you very
attention to.
much, Richard.
Cool. All right. So just hang one second. I'll say bye off air. But other than that, thank you very much. Okay. We're officially off of the air.